It is my sincere pleasure to introduce tonight's very special speaker, Dr. Lee Smolin. Dr. Smolin was born in New York City. He was raised there and in Cincinnati. He left high school early, and that's a story you need to hear at another time, but he left high school early to attend Hampshire College. Eventually, he earned his PhD in theoretical physics from Harvard, and then in 2001, he joined a handful of visionaries and became a founding member of Perimeter Institute. Lee's main area of research is quantum gravity, but certainly not restricted to just quantum gravity. He, like some of his colleagues, used to see time as imaginary, as an illusion. And Lee is here tonight to tell us how his understanding of time has changed and to give us a glimpse into his latest book, Time Reborn. So, ladies and gentlemen, please join me in welcoming Dr. Lee Smolin.
Thank you very much. Thank you. It is a great pleasure as well as an honor to be speaking to you in the public lecture series. I gave a public lecture here, I think in 2002, very early in the series. It's great to be back. It's also, this is the first talk based on the presentation of my new book, and it's a wonderful pleasure to be doing this here at Perimeter. The book, as I hope you'll appreciate from my description of it today, is bold. It has been quite frightening to write, to think through. In all my books, I don't do journalism. I don't do science publicity and science journalism. I use the opportunity to write a book to think through some hard puzzle in my professional life as a scientist. And it's always a struggle to get it right. And this book was the hardest struggle. But I'm immensely proud of where it's brought me. It's changed completely my view, not just as Greg said, of time, but of many things in addition to time in physics. So I want to give you a glimpse of the argument in the book. Let's see if this works. That, by the way, is the book as you can buy it in Canada and the United States. That is the book if you happen to be in the United Kingdom. Same book, different aesthetic. My adventure in the reality of time is a shared one. And I'll tell the story in more detail later, but this has been an intellectual adventure shared with several people that I'll just mention at the end. But one in particular is Roberto Mangueira Unger, who is a Brazilian philosopher, a professor of law at Harvard, and a politician. And he proposed to me 6 years ago that we re-examine the notion of time and cosmology and the notion of a law of physics. And we have been doing so. This Time Reborn is the first output of this, apart from some scientific papers. It's meant for the general public. It's meant for the widest possible audience. We have also, for those who are interested, a technical book, a professional book for philosophers and scientists, as well as adventurous lay people in progress, and that will be coming soon, we hope. Okay, now, science began with time. The first scientist, according to my friend Carlo Rovelli, who wrote a book about him, was Anaximander. And Anaximander, the only thing we know about him for sure is this quotation: all things originate from one another and vanish into one another according to necessity in conformity with the order of time. So scientists have been thinking about the nature of time since there was science. This talk, as well as the book, is, as I said, not a journalistic presentation, it's an argument. And it's going to ask engagement from the audience and participation by the audience. So I hope we'll have a lively discussion as a result of it. It's in 4 sections or 4 movements. The first is just the questions, because I want everybody to be on the same page and thinking about the same questions. And of course, as anything in science, the questions are more important than the answers. The questions are where we are at the edge of knowledge. And you'll see when I talk about questions that we mix questions about physics and cosmology with questions about ordinary life. And I mean to suggest that how we think about space and especially time in science changes our whole view of ourselves, our conception of our societies, of the challenges we face personally and as societies. And I mean to suggest that in the book, there's an epilogue where I go into some detail about these connections. I won't be doing anything more in this talk than suggesting there are these connections in the questions that I ask. Then I'm going to argue that the old way of looking at time, which is dominant in physics, which is basically that time is irrelevant, time doesn't exist, time is an illusion, is wrong, is based on some fallacious reasoning. And that's the second part. The third part is to introduce a new way of thinking about time in the context of cosmology. And the last part is some implications. And I understand this is going to be, I hope, exciting. This is going to be like being on a raft on a river going past some rapids. There's going to be a lot of sights we're going to only glimpse, but let's get started. Let's get started by talking about the future. In 2080, let me make the statement that in 2080, and you hear statements like this all the time, the average temperature on the Earth will be 6 degrees warmer. Now, statements like this are said all the time about the future. Is this true or false now? Is this something which is a fact or false now? In 2080, it will be a fact. Is it a fact now, or is it something which is either true or false now? Or is it something which has no truth value, no meaning to be evaluated now? It matters, I claim, for how we think about what we do about the fact that the temperature may be 6 degrees warmer in 2080, whether we think of it as something which is already either true or false, or whether we think of it as something which is not yet determined, even if you knew everything. Can we choose to influence it? Do we have freedom and agency in this universe we live in? That's the kind of question I want to raise about time. Essentially, is time real? And I'll tell you as we go along what I mean by time being real. I mean not just that we can label events that happen with dates and times. I mean something much deeper by is time real, and we'll unfold it as we go along. Or is time an illusion? Is the experience we have of being caught in time, of everything that we experience being experienced in a moment of time, which is one of a flow of moments, is this just an illusion because of our psychology or biology, our apprehension of a timeless world where truths are timeless? Or is this the deepest clue we have as to the nature of reality? The deepest experience, true experience we have about the nature of reality? That's the major question we're challenged with tonight. And what about when we say something is true? Does that stand outside of time? For example, the value of the temperature of the globe in 2080. If that is true then, in the future, is it also true now? Or is all true relative to a moment of time? One of the things that I mean by time being real is that what is real in a moment of time and only in a moment of time. Are all truths true outside of time? Or are truths true only in moments of time? Does time emerge from law? As I'll be explaining, the dominant point of view in my profession now is that the laws of nature come first and are stated in a way which is timeless, in which time plays no fundamental role, and time emerges as a kind of large-scale phenomenon, the way the temperature does, or pressure. Or do laws emerge from time, which is the view that I'll be arguing for? Is time prior to law, or is law prior to time? You may not even have thought that there's a choice to be made there. And this is one of the things that I really understood in my discussions with Roberto Unger. It's one or the other, and I'll be suggesting why as we go along. Is the future already determined? Lots of people talk about determinism. The laws of nature, if you know everything in the laws of nature, will tell you exactly what the future will be, or maybe not. The standard view among people who believe, quote, in the scientific worldview is that the future is determined by the laws of physics acting on the present, I'm going to argue that that's not the case, which means that the future is open. It means that novelty is possible. Can there be phenomena in the world which are genuinely novel? Can nature invent them, and can we invent them as parts of nature? If we knew everything there is to know about an instant, could we still be surprised by what would happen in the next instant? This is what's at stake. We have a human experience of agency, of will, of freedom. We're told that this is alien to the scientific worldview. Is it really? I want to say the scientific worldview is based on false, fallacious reasoning at certain key points. Here's a question which may seem unrelated, but is the key to the whole, to unraveling the mistakes that people have made thinking about time. Do the laws of nature apply, when we say Newton's laws about something moving, do they apply to parts of the universe, or do they apply to the whole universe? Maybe there are very different kinds of laws that apply at the scale of the whole universe. We do, in this building, we do a lot of theoretical cosmology, and most of what we do is take the laws that have been discovered by experiment to apply to parts of the universe, and just assume that they can be scaled up to apply to the whole universe. I'm going to be suggesting that's wrong. And you see what I'm doing in this section of questions is making a kind of preview. I'm indicating, putting my markers where I'm going to later come in and make arguments. In my experience of writing this as a book about science, I found myself thinking about my own life. And again, here I'm only going to suggest by asking these questions that there are consequences for how we think about our own life. One question I, at my stage of life, find I'm thinking about a lot is, do we have more or less freedom as we get older? Well, I'm not going to discuss that further. But I claim it matters how you think about the nature of time. And what is the wise response to future risks such as climate change? I claim again it matters how you think about time, how you think about these important questions of human existence. Now, physicists would claim that they know the answer, that we know the answer to these questions. Fundamentally, from Democritus and Lucretius, we have the scientific picture of the world as atoms moving in a void. Nothing fundamentally happens except atoms move around and rearrange themselves. The laws of physics, which describe how the atoms move around, are deterministic. Hence, the future is already completely determined from the present, and hence novelty is an illusion and free will is impossible. Tom Stoppard, in his play Arcadia, had his heroine Thomasina express this. She is a kind of prodigy, and she's a prodigy in mathematics as well as thought. She's a young woman studying with a tutor, and she expresses this thought. And I don't read all the quotes here, but I'll read this one. If you could stop every atom in its position and direction, and if your mind could comprehend all the actions thus suspended, then if you were really, really, really good at math, at algebra, you could write the formula for all the future. And although nobody can be so clever as to do that, the formula must exist just as if one could. This is the view that reality is completely captured by some mathematical formula. And I thought, until a few years ago, that my job as a theoretical physicist, that what I'd signed up for since I was a teenager, was to discover that mathematical formula that Thomasina, Stoppard's character, is talking about. Now, that means that there really isn't any time, because if the reality is represented by a formula, and if the future, the whole future, can be deduced as a formula from the formula for the present by some logical deduction, then the process of logical deduction is completely equivalent to the process of the unfolding of the phenomena of the world in time. If the phenomena of the unfolding of the world, things causing each other in time, can be completely captured by mathematics, then it's completely equivalent to logic. But logic is timeless. You can sit down and deduce anytime you like what the consequences are. So the world is as if there were no time. It's just a big logical deduction sitting in a world of pure timeless abstract logic and mathematics. That's the picture that underlies what I'm going to be calling in a minute the Newtonian conception of nature. Now, Sabine Hassenfelder is a faculty member at Norrita in Stockholm. She was a postdoc here and she's a blogger. And this is her response to this kind of philosophizing. She's talking about Max Tegmark, who's a cosmologist who talks about this idea that the universe is really just mathematics. And she says, Max Tegmark says the whole universe is a mathematical structure. So he must believe that he is a mathematical structure as well. And so I must be a mathematical structure. I wonder what it feels like to be a mathematical structure. Is there a problem here? Do you see what I'm getting at? What is our place in a universe if a universe is mathematics, if time is inessential because what time brings can be reproduced completely just by logic, which is timeless? Now this scientific fatalism, which is foisted off as the scientific worldview, I'm going to be arguing is based on fallacious reasoning. And one way to see that is that there are big questions about nature. The point of science is to ask questions, and there are big questions that this point of view cannot answer that we would like to know the answer to. One of them is not just what the laws of nature are. Physicists have been for several centuries trying to discover and succeeding to a large extent to discover what the laws of nature are. But as we grow more and more confident that we're on the right track, we want to know, why are these the laws and not others? And these extend to the form of the laws, the things like the dimensionality of space and time, and things like the values of constants, like the value of the electric charge, the masses of the different particles and so forth. Why has nature made these choices? Nature has made a vast number of choices in selecting the laws that we observe experimentally out of a much larger and infinite set of laws that, as far as we can tell, are logically and mathematically also possibilities. So what chose the laws of nature? Anybody know? Stay tuned. Now, laws in physics tell you how the world evolves in time. If you give it the world as it is, if you're describing a system and you give it as it is at one time, the law will tell you what it's going to be like in the future. That's called evolving in time. And that worked great to explain things, but then why was the initial state at the beginning time what it was? It tells you what the future is going to be if you know the present, but then why is the present the way it is? Well, that's because it was in the past, and so on and so forth. Now, we believe in an expanding universe with some very singular event, the Big Bang, that everything came out of. So everything traces back to the Big Bang. The fact that we're all sitting here in this room traces back to some quantum fluctuation going on near the Big Bang early in the universe. What chose those initial conditions of the universe? Why those initial conditions, again, out of an infinite set of possible other initial conditions that might have been chosen? Anybody know? If it's random, why is the universe so highly organized? Why are such highly organized beings such as us here? That's a part of the argument in the book, and that's a part of the argument that I'm not going to be able to make here, but if you can raise it again. If it's in the question session. Okay, so that was the first part of the talk. Now the second part, the old paradigm, physics of a part of the universe. So I'm now going to argue that all the physical laws that we understand well, quantum mechanics, the standard model of particle physics, general relativity, Newtonian mechanics, all only make sense when they're describing a limited domain of phenomenon. I call it sometimes physics in a box, in a laboratory or limited to a particular region of space and time. Okay. The laws, such as we understand them, cannot, I'm going to argue, be extended to the whole universe. This is an argument. I hope you get the argument. The longer form of the argument, of course, is in the book, spread through several chapters. But I'm just going to give you a glimpse of the key ideas of this argument, because this is the key to deconstructing that fallacious scientific worldview in which the world is equivalent to mathematics and therefore there is no time. The key to the argument is three more questions. What is a law of physics? Must it be timeless, or can something be a law of physics and still change in time? And are new kinds of laws needed to describe the whole rather than the part of a universe? Now, Newton gave us the paradigm for explanation of laws of physics of the kind that I'm talking about, and we call it the Newtonian Paradigm. The key is the separation of explanation into two parts, and I've just been saying it. You say what the law is, and you say what the initial state or condition of the system is, and that tells you what the final state is. You want to know where the planets are now going around the sun? Ask where were they a million years ago, and then use Newton's law of gravity and motion to go forward and reason about where the planets will be now. If you know the initial condition at an earlier time and you know the law, you can explain things now. So there are those two things that the explanation depends on: laws and initial conditions. Got it? To set up a theory in this paradigm, you have to answer two questions. What are the possible states of the system? What are the possible positions that the planets might have if we take the solar system? You say each of them could be spread out in three-dimensional space around the sun. That answers the question, what are the possible states of the system? All the ways to put the planets in relation to the sun is a possible state of the system. If your system is some quantum mechanical system, you have another kind of answer. If it's a universe in general relativity, you have another kind of answer. But for all these modes of explanation, you have to say, what are the possible states of the system? And you have to say for all time, what are the possible states of the system? It can't be that the system evolves, and then a million years later it discovers some new states it can be in. By the way, biology works like that. Biology is not a theory of the kind I'm talking about. Second question is, how do those states change in time? What are the laws that govern how they change in time? If you answer those two questions, you can set up an explanation according to Newton. The way you do that is you draw a picture of a space, some abstract space, which is just that purple or violet thing, which represents all the possible states of a system. By the way, sometimes there's a lot of words on the transparency that I don't say because they're for experts, or sometimes they're for experts, sometimes they're for the opposite, they're for non-experts, but I talk to the middle of the audience, and sometimes there's more or lower or different things on the screen, so I hope that helps. Okay. So there's a space of possible states, and there are paths through the space of possible states. The system has a history. As the planets move around the sun, they go through a history of actual rather than possible states, and that's some curve in the space of possible states. And then there's this funny thing, which is that there's an instant which is now, and that doesn't come into the description at all. So now that might be where the system is in the space of states now, but it doesn't matter for the description. Why? Because this is a model. This is not reality. For reality, there's always some time. But this is a mathematical model, and in a mathematical model, there's no time because you just draw the curves in some geometrical space, and the curve is there for always, and the space is there for always. So you see, our world, in which there is time and it's always passing, is modeled by mathematics, by geometry, in a way that removes the present moment from the world. And the key question is that a mistake? Is that a deep mistake that's misled us for 400 years since Descartes and Galileo first did that, first started drawing pictures like this of curves and spaces to represent the history of the world? Or is that a deep insight into nature, that our experience of time is really an illusion and nature is really timeless? That's the question that's at stake. Now, for you take this point of view and you take it seriously, there really is no time. There's just some mathematics in which there's a space of possible things that might happen, and a history is a sequence of those possible things happening, but there's no time, it's just a curve in a space of possibilities. And as I said, because you can use mathematics and logic to deduce what the future is going to be from the present, time has no generative role. There's no becoming in the world. There's no present moment. Time can be replaced by logic, which is timeless. Hence, there's a history, which I'm not going to repeat here, I describe some of this in the book, of people making bold statements like, well, in reality there is no time. The difference between the present, future, and past is meaningless. It's only because we're stupid, dumb human beings that we're animals and somehow we have this illusion of time. But there's a flaw in the argument. There are several flaws in the argument. One of them is that to make a case that your model has a metaphysical property which really extends to the whole universe, your model had better extend to the whole universe. Does it? Can this method of doing science that I've been describing be expanded and applied to the whole universe? It can't. And why can't it? This is the crucial step in the argument. One reason is that the space of possible states, which I had you think about, corresponds to all the things that might happen. If you have a system in a laboratory, you can go in one day and prepare it in an initial state one way. You can go in the next afternoon and prepare it in a different initial state. You can go in the third day and prepare it in a still different initial state. There's an infinite number of possible states you can prepare your system in, and then you can study how it changes in time. And that's how you separate the notion of a law from the role of the initial conditions, because you see what doesn't change when you change the initial conditions, and that's what's captured by the law. To separate the notion of a law, which is outside of time, from the role of the initial conditions, that how you set the thing up, you need many instances to try your experiment on. You need to do your experiment over and over again. It's part of the methodology of science. But there is just one universe. We don't have the opportunity of running the experiment over and over again when it's the universe. It just happened once. It's happening once. So the basic precondition to make the mathematics of the models, which allow you to have an infinite number of possible states of the system, and the experiment, which allows you to set up a system in many different ways, they coincide when it's a little part of the universe. Indeed, each try at the experiment is a different little part of the universe, and there are many of them. So a general law applies to many cases. A general law applies to many cases, but there's only one universe. So there's a problem. Now, by the way, some of my friends and colleagues, who you may have heard of in this lecture series, you may have heard from some of them directly, take this mistake and ramify it into an ideology. They say, oh well, if to do science you need many systems that are just like the system that you're describing, maybe there are many universes. Because the kind of science that we do requires many instances, many examples to separate the notion of the general law out from the role of the individual conditions. And we can't do that with the universe. So we can't make a distinction between what's a general law and what's the particular situation. And that means we can't do science the way that Newton said. Okay? Now, that's one of the arguments. There are other arguments, but that's one of the arguments of why the application of Newton's style of doing physics to the universe as a whole is fallacious, is wrong. I'm going to have one more argument in a little bit. Now, all the successful applications of this method of doing physics are in fact to small parts of the universe. When we say in this building we're doing cosmology, we really only study a few aspects of the universe, like its size or its density. That's not the whole universe either. That's just a different way of talking about a little bit of it. So we have no experience making and studying theories which are really theories of the whole universe. And my point is that because of issues like the one that I've been talking about, any theory of the whole universe that really counts for that has to be completely different than the theories that we've been discussing. Not only that, if the theories that we've been discussing don't apply to the whole universe, the whole metaphysical argument that time is an illusion is false, or at least it fails, because it's based on a false extrapolation of a system of modeling of little bits of the universe to the universe as a whole. So all the centuries of time isn't really real, the experience of time is an illusion, go by the wayside. Now, there's a dilemma which underlies another way that the application of physics to the whole universe fails. By the way, I don't know if you expected to come here and see a member of Perimeter Institute which specializes in trying to do physics of the whole universe sit here and say that everything we've tried to do is wrong, but that's what I am explaining to you. Okay. If the applications of physics so far that have succeeded are to small systems, things like what's going on in the collision regions at CERN, or in the laboratories over at the IQC when they're doing quantum information devices. Those are all little isolated subsystems where they're doing physics. Okay. There's a problem, which is that every application of physics to a small part of the world is approximate. It can't be exact. We can't model a small part of the world exactly because there's an infinite number of small ways in which the outer world messes with the world that we're modeling. We can say we're making a model of everything that's going on in this auditorium, but there's cosmic rays coming through. We can try to shield those. There's neutrinos that come through. There's gravity waves that come through. We can't pretend that any part of the world is isolated from the rest. But when we do physics this way, we do that. So everything is based on an approximation, which is fine because we know how to control those approximations. But we say, oh, we can make our theories better and better by making them, if this room is too small of a domain, let's make it involve the whole solar system. But there are cosmic rays coming from outside the solar system, let's make it involve the whole galaxy. But there are gravity waves coming from outside the galaxy, and so on until we get to the whole universe. Okay. So there's this idea that we're always working with approximations, but we can make our science better and better by taking bigger and bigger domains. But then we get to the domain of the universe as a whole, and there's only one system, and the method we're using breaks down. That's a dilemma, and Roberto Unger and I call that the cosmological dilemma. We have to live with the fact that all our models describe only approximations. When we ignore that and pretend that we can take the method of science that Newton developed that works so well for small parts of the universe to large and apply it to the whole universe, we commit a fallacy. We call that the cosmological fallacy. I have the sense that I'm stretching you guys, but this is the logical argument I want everybody to get. Are you with me? Okay, it's going to get fun in a minute. When we make the mistake that I'm saying is a mistake and try to apply the standard notion, the standard method of physics to the whole universe, we get some wacky questions like, what was time before the Big Bang? If time started at the Big Bang, what was time before the Big Bang? That's a wacky question. Or what chose the laws? As I've said, that's a question that this method can't answer because the laws are the input. Or what chose the initial conditions? The initial conditions at the Big Bang are the input. It can't answer that. Or what in the world are all those possible configurations of the universe doing if the universe never sits in them? Why do we have a theory which allows us to have an infinite number of possible histories of the universe when the universe has only one history? We end up with a lot of wackiness because we're doing something dumb. Now, that's the first part of the argument. The second part of the argument is, can we do better? And I'm not going to claim that I or we have so far done better, but I want to claim that by taking these issues into account, we can aim to do better, and we can aim to do better by taking a different approach to physics, which starts with the reality of time as the basic assumption. Now, by the reality of time, I mean the following. So now I'm going to paint you a picture of a different scientific worldview. I'm arguing that this old scientific worldview that many of us think we've been living in, a universe which is mathematical and timeless, is wrong, has broken down and failed on its own devices. And now I'm going to give you a taste of a different scientific, and I claim even more scientific worldview. Why more scientific? Because it can answer more questions in ways that are checkable by experiment. So what do I mean when I say time is real? I mean that all that is real in the present moment, which is one of a succession of moments. The experience we have of everything we experience is experienced in a moment of time is the deepest clue we have as to the nature of the universe. There are no truths, there are nothing that exists outside of the present moment. Therefore, there are no laws of nature which are timeless. If a law is acting, it must also be something that lives in time. It is something that's true now and might or might not be true later. That means that we can talk objectively about the future, the present, and the past. And we can invent laws of nature that refer to the future, the present, and the past. And it means that this idea that Thomasina so well expressed, that there's some mathematical equation which could be written down, which is a complete mirror of reality, as the philosopher Richard Rorty called it, is just wrong. It's the wrong thing to try to do. It's good for models of little bits of the universe, but it's the wrong thing to try to do if you want to do cosmology and science. The future and the past are now quite different. The past is all the things that have happened in prior moments. It doesn't exist anymore, but we can have evidence of it in the present, and we can reason from that evidence about what happened in the past. The future is open, at least partly, because if there are no timeless laws of nature, then laws of nature can change, and if laws of nature can change, then they may change in ways that are not predictable. Otherwise, there would be just another law of nature that would predict how it would change. So the future is genuinely, at least in some ways, unpredictable, which means that there is real novelty. Now, Einstein is a good figure to discuss the transition I'm talking about, because Einstein was genuinely ambivalent about the questions that we're talking about. He's very famously quoted here. This was in a letter to the widow of his best friend after his friend had died, and he wrote to her to console her, and he said, "People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent an illusion." And he went on to say that therefore it's an illusion that our dear friend is departed, is past. Because the idea that life is at one time and is gone at another time is an illusion. It's just part of the illusion of time. There's a tremendous consolation in this picture. And Einstein embraced that. But he also, we know from another friend of his, the philosopher Rudolf Carnap, was deeply disturbed by the loss of the moment or the now in the description of science. As I argued earlier, as I showed you, when you describe motion mathematically, it becomes timeless, and the now, the experience that we all have of the present, of the now, has no place in that mathematical description of reality. And I'm not going to read these long quotes, but Einstein mourned that and regretted that. The absence of the ability to talk about the now in a scientific way. Now we begin the search for a new approach to physics and cosmology that can incorporate the now, and here's how I propose to do it. First, two theses or two principles. One of them is that there is just one universe. And this has two reasons for positing it. One, it cuts out all that multiverse stuff which is not science, I claim. All this stuff about speculation about our universe is one of many universes which are unobservable. It just cuts that out at the beginning and says, no, the point of science is to explain the universe we observe ourselves to be in. But it also has a deeper implication, which is that there is nothing outside the reality that we observe. Not even laws of nature that act as if from outside the world to make things happen in the world. If there's regularities in the world, they must be due to things in the world. And there's no other world of mathematics where a truer, purer notion of reality lives outside of time. There's just the world that we live in and experience. That's our job as scientists, to explain it in its own terms, in terms of what it offers to us. The second principle, that time is real, which I've already mentioned. These two principles are the basis for starting a new approach to cosmology. They forbid, and I guess I've already said this, they forbid us to have this ambition that what we're trying to do is transcend reality by discovering some mathematical model or some mathematical equation which describes perfectly reality. It just rules that out. That's the basic ideas that we're going to go on. And in the next 15 minutes or so, I'm going to describe some opportunities that this new point of view opens up. Because I'm talking, I understand here, let's take a deep breath. Because this has been a lot of blah, 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 right? This has been a lot of philosophy. Okay. And you guys are here, and we're here in this building not to do philosophy, but because we're very curious about nature. We want to understand things that we observe and experience. We want to know more about the world. And the point of science is to expand our understanding of the world. So even though I'm doing a lot of philosophy and talking in some ways as if I'm a philosopher, I'm not really a philosopher. It's all in the service of looking for battering rams and arguments to bang up and bang down old ideas and try to introduce new ideas. The philosophy, philosophers would be and are running and screaming when they see this stuff. Because this is not pure philosophy on their terms. It's philosophy in the service of science, and the goal of science is to increase our understanding, our ability to answer questions. So I'm claiming that the old point of view about physics, in which time was fundamentally absent, has reached the limit of its success. It's been enormously successful. It's been deeply successful. It's underlined all the technology we have and all the science that we have for 400 years. But now that we can ask questions at the scale of the whole universe, and now that we can ask not just what are the laws, but why are those the laws, it's run out, it's ended its run. And I want to show you that if we start with this new approach, embracing that there is a single universe to be explained on its own terms and embracing the reality of time as part of that universe, we can do better science, we have a better chance of answering those mysteries. But now the blah, blah, blah stops, and I have to show you some science. So that's what I'm going to be doing in the last little bit, implications. If time is real, we can use it. I'm going to talk about 3 questions, not in a lot of detail because I don't have a lot of time, but I'm going to talk about 3 different scientific mysteries and puzzles that I believe that this point of view will help elucidate. And this is also the content, of course, of my scientific work. Every time I write a book, it changes completely the direction that I'm going in science. And what I'm describing now is work in progress as a scientist. So if time is real, we can use the fact that time is more basic than law to try to understand why these laws are true and not other laws are true. And the key point is that there is nothing true outside of time, then laws are also things caught in time, and laws can change and evolve. Now, we observe, looking back, almost to the Big Bang. We observe, as you know from the cosmic microwave background, to a few 100,000 years after the Big Bang, and we don't see any evidence for the laws of nature changing over that scale. So if the laws of nature change in a way that helps us explicate where they come from, It must be before the Big Bang. There must have been a world before the Big Bang, and the Big Bang must have been an event which changed the world, not the beginning of the world. And that gives an opportunity to talk about how the laws might have changed from before the Big Bang to after the Big Bang. And if we can do that, we can imagine a succession of such Big Bang-like events where the laws changed. Now, the idea that the evolution or the changing of laws is the key to understanding laws is not my idea. I really wish it was. I had the experience of having that idea as if it were mine, but then my first book was partly about that, and as I was writing it, somebody sent me this quotation from Charles Sanders Peirce in 1893, an American philosopher. Okay? And what he says here, I'll read some of it. To suppose general universal laws of nature capable of being understood, okay, but not being explained, is not a good place to be. I'm translating to modern English. It ain't a good place to be if you're a scientist, to know what the laws are but not know where they come from. If you think you know something, you should be able to explain why those are the laws and where they come from. And then he says, in the red there, now the only possible way of accounting for the laws of nature is to suppose them the result of evolution. That is the Darwinian perspective, that we understand so many questions about life, about living things, because of their history, because of how they came to be that way, has to be applied to the laws of nature as well. My friend Roberto Unger puts this in an even more drastic way, and I'm not going to read the whole quote, but I'll read just the last line of the first paragraph. Only a relative distinction exists between a law-like explanation and narration of a one-time historical sequence. That, as Roberto is saying, there's not an absolute distinction between giving the laws and giving the narration of what happened in the history, because to understand the laws, you have to give them a history, and you have to discover through observation what their history was. Now, turns out other people had this idea also. Paul Dirac, who's one of the inventors of quantum mechanics, said at the beginning of time the laws of nature were probably very different than they are now. We should consider that the laws continually change. Richard Feynman, who is the great American scientist of the post-war era, speculated, I found this in a video which is online. He says, the only field which has not admitted any evolutionary question is physics. Here are you have to imagine this with his Brooklyn accent. Here are the laws, we say, but how did they get that way? In time. So it might turn out that they are not the same laws all the time after all, and there is a historical question, an evolutionary question in physics. Okay. Now, I've been exploring since the late 80s ideas about how the laws might change and evolve in time, and how we can test such ideas. And I'm going to mention here briefly two ideas I've thought about, one from the early 90s called Cosmological Natural Selection, and a new one called the Principle of Precedence that's just from this year. And I'm going to just give you a taste of these ideas, and I'm just going to state that both of these have implications that are checkable by experiment. So this is real science, even though it's going to sound a little nuts, if you're used to science being about the discovery of timeless laws that never change. Okay, so 3 minutes to each of these, and then we're concluding. Okay, are you all with me? Okay, this has been not what you expected, I'm sure. It's not what I expected when they said to me, you know, you should write another book. Your last book did okay. Which is how you get sucked in. Okay. The principle of precedence. In quantum mechanics, we prepare systems and we measure systems. And there's a funny thing, which is if you make a measurement, you prepare a quantum system, and then you make a measurement, and the outcome is statistical. It's not determined. You've probably heard a lot about quantum mechanics. If you ask, where is the electron in the orbit around the hydrogen atom, it could be many different places. It's not determined. There's a statistical distribution of outcomes. Okay. But if you prepare a hydrogen atom 50 years ago and you look for where the electron is, you get the same statistical distribution that you do now. And that you will, we're confident, in 100 years, you'll get the same statistical distribution. So even though the outcomes are statistical, there's something that doesn't change in time. Why is that? Why are phenomena reproducible? Well, here's the standard answer. The standard answer is, well, there's a law of nature, and that sits outside of time. And that acted 100 years ago, and 1 billion years ago, and 10 billion years ago, and it acts the same way now, and next year, and 1 billion years from now, it'll always give the same outcomes. It'll always give the same statistical distribution of outcomes. Because there's a law of nature that is outside of time. But that's a crazy idea. What is this thing, this belief that there are things which are outside the universe, which are outside time, which are metaphysical, religious-sounding things, laws of nature that act to make things happen? Where does that? That's a wild, crazy metaphysical idea, isn't it? Maybe we don't need it. Because all we need is the idea that nature repeats itself. Maybe if I do an experiment now, I'll get the same likely outcomes that I got the last 1 billion years the experiment was done, because maybe the experiment just looks to the past and says, there are all these instances where this same experiment was done in the past. I'll just pick one of them randomly and give me the same answer as then. There doesn't need to be all these different laws of nature written down in a complicated way. It just has to be the ability of any system, when confronted with a question, to know about similar systems that were confronted with the same question in the past and pick randomly one of the answers that was given in the past. This is called the principle of precedence. Okay. Turns out, although again I didn't know it at the time, Charles Sanders Peirce thought of this first. Okay? What's beautiful about this is that there is no metaphysics. There's nothing acting from outside the universe to make things happen. There's just the universe, things that happen in the universe faced with a question, looking back at earlier systems faced with a question and picking randomly one of the answers. Okay? This is testable because I got to go to my friends at IQC, where they make quantum systems which are so complicated but still quantum mechanical that they've never been made before in the history of the universe, so there is no precedence. So then anything can happen, maybe. And I had conversations with people at IQC about whether they could catch that. Of course, they say the problem is that the first 100 times they do an experiment over there, anything comes out anyway because they don't do it right. It takes them a few hundred or 1,000 tries to get it right anyway. So how do you tell that kind of randomness of making the experiment work from the kind of randomness that this principle would say is deeply in nature? Okay. Cosmological natural selection. This is an idea that I published in 1992. Okay. It makes cosmology work like biology. We want to understand why the laws are what they are. Imagine that the universe can reproduce itself. How could it reproduce itself? There's an old idea which is around since the 1960s that every time there's a black hole, there's created inside of it a new universe. There's a place inside a black hole where time ends, called the Singularity. At the beginning of the universe, as we observe it, there's a place where, if we model it with general relativity, time begins. You can kind of stack the place where time ends onto the place where time begins, rub out the difference with some quantum mechanics, and evolve through time ending to time beginning again. And actually, in 1992, when I published the first paper on this, that was pretty speculative, but now there are good models of what quantum mechanics does to these places where time begins and ends in quantum gravity, and it looks like a good idea. It looks like it's reproduced by the detailed mathematical models. Of course, not experiment yet. So our universe, let's just take that as a postulate, that the universe reproduces itself every time there's a black hole. Our universe has a hell of a lot of black holes in it. How many? About 10 to the 18 or 10 to the 20 so far? That's a lot of black holes. Why? Well, just hang on for a minute. Okay. Let me make the assumption, another assumption, that when the new universes are born, the laws change ever so slightly. Maybe the masses of the elementary particles change a little bit, or the strengths of the electric force or the other forces change a little bit each time that happens. So the new universe is slightly different, only slightly, from the parent. It's as if in biology there's a little bit of mutation every time. So now, those are my two assumptions. What are the consequences? Well, then there's a lot of universes around, and I apologize for that, because that bothers me, that I have to talk about a lot of universes. But they're not sitting unconnected to each other like some other people's multiverses. They're all in a lineage, connected together by parentage. Now, pick a typical universe out of this collection and look at its parent. Is the parent likely to have had many progeny or just a few? Well, many, because those universes that have many progeny reproduce themselves a lot more than universes which have just a few progeny. So if you're a typical universe, it's most likely your parent universe had lots of progeny, but you're only slightly different from that parent universe, so it's most likely you're going to have lots of progeny too. Just like biologically, each of us is really fine. We're each the result of billions of years of natural selection that make us really good at surviving and reproducing. So we do it well. The universe, it claims, is also the result of a long lineage of universes that have reproduced prolifically. So our universe will reproduce prolifically too. That means the laws of nature are tuned to make lots of black holes. That's what it says in red there. This explains many features of the world. And I don't have time, it's a different talk, it's a whole hour talk in itself to bring this out. But this explains things like why carbon and oxygen are plentiful in the world, or why the strengths of the fundamental forces are what they are. You can all tie it down to what's needed to do to make lots of big clouds of cold gas out of which lots of massive stars are made, which is the route to supernova, which is the route to black holes, to many black holes. So many things are explained, and it makes some predictions, not many, but it makes two real predictions which have been tested by observation over the last 21 years since this paper was published, and they've held up. One of them about how massive a neutron star can be, and the other one about the phenomenon called inflation. So I don't know that I believe that this theory is true, but it's very possible that in the last 20 years the theory could have been proved false. So this theory satisfies an important criteria enunciated by the philosopher Karl Popper, which is that it's falsifiable. It can be shown false by a real doable experiment. It's vulnerable, because we can only by developing theories that are vulnerable to being shown false can we increase our knowledge about the world and do science. And this theory has that property, and it's the only theory that's been proposed that explains why the laws of nature are what they are that has that property. Doesn't mean it's true, but it could be false. Okay. Now, there's a third claim I want to make, and this is recent work with Marina Cortez, that from the point of view of the reality of time, we can understand something else very basic about our universe, which is why it's so asymmetric in time. Why the past is so different from the future, why so much of phenomena are not reversible or irreversible. But I don't have time to talk about that. But I'm very excited about it. So if somebody wants to ask me, I can talk about it. Okay, to conclude, the hypothesis of the reality of time offers opportunities to search for new explanations for unsolved foundational questions. To explain the selection of laws due to evolution in time. Once you get out of this idea, and it took me years of thinking about it and writing this book to get out of it, but now the idea that the law of nature could be unchanging in time, I just go, what a silly idea. How could there be something which is true, which is outside of time? Whereas when I started, oh my God, am I saying that a law of nature could change in time? That just goes contrary to everything that I've ever been taught. So I've been through a renewal of thinking, and I believe, although I cannot claim that it's been successful science, I believe it has the possibility of leading to successful science, the idea that laws can evolve and we can study how they evolve in time. And thus get insight to why our universe is the way it is and not otherwise. New approaches to the foundations of quantum mechanics, such as the principle of precedence I talked about very briefly, is a new approach to understanding the mysteries of quantum phenomenon. New approaches to explaining why the universe is asymmetric in time to so-called arrows of time. So those are some of the scientific directions that are growing out of this way of thinking, this new scientific worldview based on the reality of time. If laws evolve, then time must be real. Just here, 2 slides as to what this means in the overall. Time does not emerge from law, as many of my colleagues say. Time is what remains of nature after the limits of laws are surpassed. If laws can evolve, then they may be able to evolve, as in the principle of precedence, in ways that are not predictable. So the future may be genuinely open. We may be liberated from this notion that the future is already determined. So we can't, in some metaphysical sense, do anything about it. Nature may have a genuine element of freedom, and surprise and novelty may be real and not illusions. It may be possible for nature to do things that were unpredictable on the basis of its past, and it may be therefore real for us to be able to invent novel ideas, novel games, novel solutions to problems. This, however, is science. It leads, I claim, to a more testable attempt at cosmology than does the older metaphysics based on timeless law. So what does this mean for us? The future is open and yet to be made. We can choose to influence the future. That's not real. That's a moral choice we have. And imagination is not just fun, but an essential part of reality and our survival. Thank you. Okay, thank you very much. Now I get yelled at.
So, Lee, the first question from our online crew, Dr. Cuspy asks, isn't this whole discussion really about putting the scientist/observer inside the universe, and then in parentheses, at last?
Yes. Yes, thank you. Thank him, and thank you for that question. If another way to say, I couldn't say everything, that's in the book, that's in the thought that led to the book in an hour. Another way to say it is that the kind of science that I've been criticizing always implicitly has the observer outside the system being studied, which is no problem if the system you're studying is in a laboratory, because the observer is outside the system. It corresponds to what you're doing. It's only when you try to scale up that way of modeling the world to the universe as a whole that there's this uncomfortable feeling, where does the observer go? If your system you're studying is the whole universe, where does the observer go if you're using a method which assumes that the observer is outside the system? And if you ask, how can you do cosmology, study the universe as a whole, but allow the observer to be part of the universe? That's a different way to ask what I'm doing. And part of how you would situate the observer inside the universe is situate them in time. Don't ignore the fact that we observers are always situated in time. That's part of experience. Now, there's a theological discussion which parallels the discussion I'm having. And I'm not interested myself in talking about the theological discussion, but just to mention, from friends in theology, there are parallel discussions in theology. And the only reason why I mention that is that I worry about sort of unconscious leakage from theological issues to scientific issues, brought about because the people who invented this way of doing physics were quite religious. People like Isaac Newton, who was deeply religious. And so if there's a parallel to religious dilemmas and theological dilemmas, it's not an accident. But I'll stop there.
In systems where evolution happens, the reproducers are following some principles. So I'm having trouble understanding, if the laws of nature evolve, then what determines the principles that they evolved by? Meta laws, or?
May I come back here? I set you up to do that, right? Because I'm all prepared to answer the question. The evolution of laws raises a big question, the meta-law dilemma. Let me state your question as a dilemma. If laws evolve, there either is a meta-law by which they evolve, or the universe is ultimately lawless. Suppose there is a meta-law. If you follow that hypothesis, you lead yourself right back to the same dilemma, what we call the cosmological dilemma. But if there's no meta-law, then anything can happen. You might be nervous. So in either case, a rational explanation of the world is stymied. That's what Roberto Unger and I call the meta-law dilemma. And it is a dilemma, but there are two kinds of dilemmas in the history of science. There are dilemmas that are just logical puzzles, or there are dilemmas such that there really is a third option. And the way that science develops is it discovers that there's not really a contradiction, there's a third option hiding in the uncomfortable feelings, and progress consists of discovering that third option, and that's what I believe. I think it arises in a particular form of law. If we assume that the meta-law has the form of this Newtonian paradigm for laws, then it arises, but it can be avoided, we believe. And there are some possible resolutions, and some of them are listed here and they're described in the book. I think I won't. It would take me a few minutes to go through each of them. But let me just make an outrageous polemic statement that I believe that the success of cosmology and physics in the 21st century will ultimately depend on finding the correct resolution of this dilemma.
Let's have another question from inside the theater, right here.
Do you think the following statement is true, that time only exists in the human mind?
No.
Okay.
The whole point of thank you for that question. The point of the talk is that that's what Carnap in all those quotes tried to tell Einstein. And no, I think that our experience of time is the deepest clue we have to the real nature of the world, that time really exists in the world.
Okay, I think I'll go to the online questions. We have a question from Lev Goldfarb. The question is, do you allow for the possibility that to deal with time, we need a fundamentally new formal language completely outside of present mathematics?
So we thought about that question. And of course, the right answer to a question like that is we don't know. Lou Kaufman, who's a very eminent, influential topologist, has speculated about that there could be ways in which, if you stray into areas of mathematics where contradiction is allowed, so that you run one of these arguments where you run into a statement, then its negation, then a statement, then its negation, which are just supposed to be excluded from mathematics, that could be creating some kind of motion in time. And what do I really think of that? What I really think about that is that it's not going to work. It sounds good. And here's why. Because when I say that time is real, I'm pointing to the world having a property that no mathematical object can have. And I need to name a property, and then I'll convince you that the world cannot be modeled by a mathematical object. And here's one, that it's always some moment. It's always some moment. Here in the real world, it's always some moment, and then it's gone, and then it's the next moment, and then it's the next moment, and it's the next moment. And mathematical objects, by definition, are timeless. They have properties which can be examined and verified at any time. So, if there is a kind of logical mathematical structure that is so weird that it's not timeless, I don't know why it would be called mathematics. but stranger things have happened. So please feel free to invent something along those lines.
Thank you. We have time for 2 more questions, so why don't we have both of them from inside the theater?
It's good to hear you recognize the reality of time. What you didn't talk about was time dilation, the myth of time dilation. I think that needs to be blown as well. What do you think of that?
I disagree. This is an important point. The special relativity may be superseded, but it's holding up enormously well under experiment. Giovanni Emiliano Camellia is here. I'm very honored. He happens to be visiting from Rome today. And he and various friends of ours have been trying to transcend special relativity for years, and we keep being knocked back by experiment. To the extent that we do anything worth talking about, we're knocked back by experiment, and the experiments have shown that special relativity is true to tremendous precision. It may ultimately be superseded, but it is true. It is so far holding up tremendous. Do you agree, Giovanni? Yeah. And if special relativity is to be superseded, it's going to be subtle. It's going to be subtle, and it's going to be in some way that permits its tremendous success. Anyway, that's my reaction to that.
And let's have one final question from here inside the theater.
I actually have 2 questions,
Okay.
but you may choose to answer either one.
Or none.
Or I hope for some answer.
Sorry, I didn't mean that.
Well, so my first question is related to the question you answered before. Okay? If the time is not just in human mind, then should we expect to empirically detect the existence of the present moment?
And what's your second question? Give me both at the same time.
Okay. And the second question would be, since science in general rejected the idea of existence of ether in space, the medium that would allow to force gravity force to propagate, then it seems to me that the idea of physical space-time or quantum space composed of some elements like gravity loops or quantum loops is very close in principle to the idea of ether. So would you think that it would be possible to have completely empty space and have gravity as an interaction that would not require existence of any medium at all, like space-time or quantum loops?
Oh, okay.
And I'm finishing.
Okay.
And for example, the gravity could be the result of quantum entanglement.
So your second question is really in the direction of research, and there's some discussion in the book about different approaches to quantum gravity that address questions like that, whether space is emergent from some more fundamental structure, as some of us in different ways study here. There are research programs called quantum gravity, or spin foams, or some versions of string theory. So we address questions like that in the research, and the relevance for the issue of the reality of time is discussed in a chapter of the book. And let me leave it there. And I wanted to answer the first question, but can somebody remind me what it was?
The empirical detection of the present moment.
The empirical. Well, we are empirically detecting the present moment all the time, but what would make it scientific is if there would be a form of a theory in which the present moment played a distinguished role, distinguishing the past from the future, and in the principle of precedence, as I described it, it did. It's impossible to state that version of physics without talking about now and distinguishing it from the past. So if such a theory made predictions which were confirmed experimentally, that would be support for the idea that the present moment corresponds to something real in nature.
Ladies and gentlemen, Dr. Lee Smolin.
Thank you.
Good speech you wrote.